lava flowing over people's houses. That's literally a couple of miles from the main road across the island. And
yes.
So I was really surprised how close it was to places I'd visited just 2 or 3 years ago.
Well, the road to, is it Puerto Neos?
Yeah.
That's been virtually cut. I think it was about 50 to 70 metres from the lava last seen. They're building a new road, but they reckon it'll take them a month for a new track.
Yeah,
but
well, it seems to be, it's cut off that whole end of the island, and the only other way is round the south side of the island, which has got a very poor road, as I recall. No one ever usually goes that way.
The north side, you mean?
Yeah.
Round LP1.
Hi, Rachel. Yeah. Nice to see Rachel as well. Seeing all people in real life that we don't normally see on shows. So it's nice to see you all. Now, I'm going to ask you to, I'm going to start the meeting now. And this is where I kick off. Nice to see everybody. If you'd like to use your speaker view, then you will get just the show coming up. There's a lot of controls that you can use yourselves if you're not familiar with Zoom. Got a small attendance at the moment, but that's not surprising at this time of the day. And so I'm sure it will build up as things go on. So it might be better if you all switch off your videos, and then we don't have too many competing pictures. Right, thank you very much. More people joining all the time. We've got 31 participants, actually. That's good. That's about what we have at a regular Preston Montford. Now, just to set the scene, Preston Montford, you can see it there behind me. This is Preston Montford Hall. And that is a view that we had when back in 2010, we actually had snow at Preston Montford on the Preston Montford weekend. It was the 28th of November. And of course, that can easily give rise to quite wintry conditions. And at other times, like looking outside today, it would be lovely and mild. So it's a good time of year to hold a weekend course, because you have the, usually it's intended to be an observational course, of course, and we use telescopes in the evening. And the place itself, Preston Montford Hall, has very nice, good sort of solid catering facility, shall we say. There's always plenty of food to eat, and the rooms are now quite comfortable. When we started going there in 1977, a lot of people had to share rooms in the hall behind. They were often things like bunk beds. It was mostly used, it still is largely used, the hall as a field studies centre. That's the people who run it. And it is used for a lot of school field trips and university field trips. And of course, they are accustomed to slightly less luxurious accommodation, those of us who are of older years. But these days, they have plenty of accommodation of quite reasonable quality, not to mention comfortable, for those of us who prefer something a little less rudimentary. So it's a great place to hold a weekend, observing weekend. It's fairly well placed in the middle of the country near Shrewsbury. A lot of people can get to it, and the reason that the skies are reasonably dark, as you can see here, Orion there showed up quite well, and a lot of people say wow when they see the sky. Those who come from mid Wales might say, oh, this is nothing like as good as I'm used to, but nevertheless it represents quite a good sky for most of us who don't get the chance to see a good sky normally anyway. Now, this weekend, as we know, is replacing the usual live residential weekend, and we hope that it gives people a chance to enjoy what we would normally do. We've got 6 talks. They are condensed down from the usual 2 days of talks that we have at a regular Preston Montford, where we can go into greater depth. So this is really just skimming the surface, and of course we're missing out on the on a lot of the social interaction, but I hope we will be able to achieve a bit of that during the course of the event. So now I'm going to share my screen. Oh, I haven't started my PowerPoint yet. That would help, wouldn't it? Let's just go back to that. I think has everyone got their microphones off? I can hear a little bit of noises off in the background. I should be able to switch everybody off automatically, but I'll leave it up to you. But just check your microphones are off and you're on mute, because that does sometimes create lots of noises off when you don't expect them. Right, just starting my PowerPoint now. Here it's coming up, and I'll start to run it, and then I should be able to share my screen. It's about the movement of the planets, but I've given it a rather jolly name. I'm looking at the wrong screen there myself. Hold on, everyone. I've got lost. Got YouTube up. Says I'm sharing screen, but I think I'm sharing the wrong screen. I'm going to stop that and start again. Ah, that looks more like it, doesn't it? Okay. Participants can now see your application. Right, so I've called this mysterious apparitions because it's one of those, some of the words that we use to describe the positions of the planets are ones which we use in real life, in everyday life, to describe other things. And one of them is apparition. And particularly around Halloween, people think of an apparition as something unworldly, and it is something that shouldn't be there. But apparition simply means, and I'll define these terms in a minute, the appearance of a planet over the course of a year. Now, I've put up a plan of the solar system. This is slightly unusual from the one you see in a lot of books, in that it's actually to scale. Not the two scales are different. The scale looking at the position of the planets from the sun is actually accurate insofar as the distance from Mercury, Earth, Venus, Earth, Mars, and then the long gap to the Jupiter and the other planets. Those distances are accurate. Those four internal planets, inferior, the four terrestrial planets, as they're called, are quite bunched together. Then there's a big gap where the asteroids are. Then there are the outer planets. And a lot of diagrams in books don't like to bunch the orbits of the inner planets together as much as they are. You can see they're really quite close to the sun. But what the scale of the diameters of the planets, they're also to scale. The sun is to scale with the Earth and Jupiter and all the others, but it is a different scale from that of the distances. So I think that's worth just pointing out. When you get a lot of diagrams in books, they are always out of scale for an obvious reason. And you can see the size of Mars, say, compared with the sun. To represent the two on the diagram accurately is virtually impossible. So let's go on to talk about, as the planets orbit the sun, they move in and out of the visibility from Earth. This so much is obvious, but people that don't always understand just when and where they're going to appear. And sometimes people see you and say you're an astronomer, and you, what's that star over there? You say, oh, that's Jupiter. They say, how do you know that? Well, of course, it's our job to know. It's something that we know, we look to see where the planets are occurring. And so the appearance of a planet during when it's there, when it's visible, is called an apparition. So you might have an apparition of Jupiter. That is the period when it is visible. And I'll go into when it's visible in a minute or two. And that's simply the apparition. And we use these terms fairly glibly in popular astronomy and magazines, but they are not always well defined. And we have some other terms, apparition, as I've said there. We also have opposition, which is the period when the moment where the planet is opposite the sun in the sky. And I'll show you some diagrams about that in a minute. We have, my slide's not moving on. We have conjunction. And that's the moment when the planet has, there are two definitions. It's either the moment where the planet has the same RA as the sun, same right ascension as the sun, or that of another planet. And so these two definitions can sometimes cause confusion. And finally, we have an appulse. I'm not going to deal with those. That's the apparent close approach of one body to another as seen in the sky. But those, the appulse and the conjunction are two terms which are often slightly confused, as I shall say right at the end of the talk. Okay, looking at the orbits of the planets there, as I'm sure most of you know, the two planets to the closest to the sun have different apparitions from those farther from the sun, and they are called the inferior planets. Another term which we use in everyday life to mean something slightly different, which just means that they are inwards of the sun, of the earth in their orbits, and the planets outside the earth orbit of the earth are called the superior planets. Nothing great about them, but that's just the way they are described. Now, these two planets, Venus and Mercury, both orbit the sun more quickly than Earth, and of course they're both, as you know, only visible roughly in the same direction as the sun. And I missed out on the caption there. That means that they orbit the sun more quickly. The sun, Mercury orbits the sun 4 times for one orbit of the Earth, and Venus once every 8 months. So although they are going round more quickly, the Earth is already moving round as well, and that means that we don't see Venus once in the same place in the sky every 8 months. It's going to move from time to time because according to the season, because the Earth is also moving around. So let's have a look at this in some detail. There's Venus as it appears in the sky, a very bright and beautiful object. The planet Venus, regarded as the most beautiful by poets and authors and so on, but not necessarily by astronomers, although it's pretty lovely. Each inferior planet can either appear in the evening or the morning sky, and each apparition is known as an elongation, another term which can cause a bit of confusion, as the planet appears to move away from the sun, reach a maximum, and then move back towards the sun. And there are 6 or 7 of these of Mercury a year, and a bit more than 1 of Venus every year. So we don't necessarily see, in the past year, we've hardly seen Venus at all, although it has had one of these apparitions, an elongation, and I'll mention that in a minute. This is what we would normally expect to see of an appearance of Venus, and that is something you would never normally see with the sun below the horizon, and there is the orbit of the planet going like that, and at a certain point it reaches its greatest elongation, greatest distance between the sun and the planet, and that is when we get to see it. Now, in the case of Venus, we do actually get to see it occasionally in a dark sky, but more often than not it is still in a twilight sky, and this makes it slightly difficult to observe because it's usually in a fairly bright part of the sky and also fairly low down, but there are ways and means of observing that, as I suspect Martin will mention in due course. And here's Mercury. Now, this is a view which you would not normally see. This was put together by a Spanish observer who claims he observed Mercury on each occasion that you see there and put them all together in a composite. That's a lovely photograph. And I know Paul Sutherland, for example, has actually been watching the latest apparition of Mercury in the morning sky, and he was surprised to find how long after the actual moment of the greatest elongation he could track it in the morning sky. He's very fortunate to have an east-facing house over the sea of the English Channel, and he can actually, if he gets a lovely clear morning and he gets up early, he can actually see Mercury really quite low in the sky, in the twilight sky, for about 2 weeks that it appears, as you can see by counting the number of dots there. Now on to Venus. Now here's a lovely graphic done by Dave Smith of Malden when he photographed. I think he may have completed a few more dots there, a few more actual images. It shows you the difference in appearance of size of Venus over its apparition. So when we first see it, it's not far from the sun. Again, these pictures are not to scale. Just imagine if Venus went in front of the sun and it would completely blot it out. So the scale of the sun and that of Venus itself are different, but it gives you a graphical representation of the appearance. And the two halves are matched really. So it appears as a small dot in the sky in the, if we're talking about evening appearances, a small dot in the sky, quite low down on the horizon. And it's moving quite slowly at this point because it's on the far side of the sun, and it's quite distant. And then it, over a period of months, it gains in phase, it gains in size until it reaches this point, which is known as dichotomy, when it's a half phase. And it actually does look just like a little miniature moon through a telescope. And you show people that through a telescope and they say, well, that's the moon, it's not Venus. But there we go. And then we are now just past that stage in the current apparition of Venus. And I forget what exactly the phase is at the moment, but it's coming to this sort of phase. And by the end of this month, it will start to get to be a noticeable crescent. And you can actually see that crescent with binoculars during the end of this month and into December. You will be able to look at Venus, which is by a trick of geometry actually getting higher in the sky at the moment. That's something I dealt with at the last quarterly meeting of the Society back in the end of October. I showed you some pictures of that. And it will appear as a thin crescent, and that's well worth looking for. So do keep a lookout for Venus in the next few days and watch its phase grow. Then it passes not actually in front of the sun, but usually one above or below, as it will this time. And then it is visible a few days after, about a week or two after its appeal on one side of the sun. It then appears in the morning sky, and the whole sequence of phases reverses. So Mercury does that as well, but Venus is more observable because it gets farther from the sun. When Mercury has had its crescent phase, I'm not sure that maybe some people have observed it, but it is then very close to the sun. Bear in mind that Mercury will be much closer, and it would only be visible for a short time when the conditions are most favorable as something like a crescent. So most people see Mercury only over that range of phases, not a very great range. So that's what we call when the planet is east of the sun, that is on this side of the sun here, it is called the easterly elongation, and it's visible in the evening sky, which is very convenient because east and evening both begin with the letter E, so that's easy to remember. But when it's in as it said, well, I've said that already, and then westerly elongation of both Venus and Mercury is visible in the morning sky. And okay, W and M don't necessarily start with the same letter, but you turn one letter up and it's the same letter. So you turn the W of Western upside down, and it's visible in the morning sky. So if you want to remember the two, that's the way to do it. And it gets kind of confusing because the easternal elongation, it's visible in the evening sky, but it's visible in the west, and because that's where the sun has set. So that's where the confusion arises. So when the planet is to the east of the sun, it's the evening elongation, and that's the way to remember it. Here's a list of the apparitions, the elongations of the two planets, the two inferior planets over the next year. I put in the most recent one just a couple of weeks ago when Venus was at its greatest eastern elongation, and it is there in the evening sky for you to look at the moment. Then it goes in, I haven't made a note of when the moment of conjunction, when it's right in front of the sun. I haven't made a note of that, but then fairly soon it goes in front of the sun, and it will be visible in the morning sky, and it will be then at its greatest western elongation in the morning sky on the 20th March. And then there's a big gap of over a year before it gets to its eastern elongation again. The picture by Dave Tyler, incidentally, shows a fairly rare circumstance of both Mercury and Venus in the sky at the same time, and the crescent moon thrown in there as well for good luck. It was taken by a friend of mine, Dave Tyler. He literally lives about 400 yards down the road from me, which is very convenient. And he took this picture, I think, from his back garden. And so he's got both Mercury and Venus there, I think, in the evening sky. So those are the appearances of Mercury over the next few months, over the next year. And the next time you'll see it as an eastern elongation is on the 7th of January. So look for it a couple of weeks either side of that, if you get a good low western horizon after sunset. Now moving on to the outer planets, the superior planets, and talking about Mars. And I'm going to be talking about Mars here and the movements of Mars, but they apply to Jupiter and Saturn and Uranus and Neptune as well. So for the superior planets, Mars outwards, the situation is quite different in terms of the way we observe them, when we can observe them. And I've got a graphic here which I've done, which shows you the situation. This incidentally is based always with the Earth in that position. And I'm showing Mars. Mars, of course, moves around the sun in this direction here, but the Earth is moving faster in its orbit. The result being that we seem to catch up Mars. We catch Mars up over a period of months. And so all these pictures are from the same viewpoint of the Earth. So there is Mars at the time when it first becomes visible it first becomes visible during one apparition in the morning sky. And as you see, this is the eastern sky of the Earth. It's the morning, and it's visible quite low down, quite close to the sun. Then as time goes by, visible as a tiny disk, and then the Earth is catching up. Now remember, I said this is from the viewpoint of the Earth. So Mars is shown as having moved that far around its orbit, but actually it's the Earth catching it up. So this is from the same viewpoint again. And at this point, Mars is more visible. It's got a bit closer and it's visible slightly higher in the sky. Then a few months go on and we get to what's known as opposition, which is where the planet is at its closest to Earth. And at that point, it's visible in the directly opposite the sun, and it's called opposition because it's opposite the sun. And this is the best time, of course, to observe because it is closest to the Earth, and it's also highest in the sky as we see it. Instead of crouching down in the morning sky, it's then in the midnight sky. That's midnight GMT or universal time, which might in the summer be at 1 in the morning. So opposition, you think, would be a good time to observe it. That's when everybody should be out there observing. And of course, the dedicated Mars, Jupiter and Saturn observers will be observing around opposition. But for most of us, it's not so convenient, particularly in summer, to get up at 1 in the morning to see the planet highest in the sky. So we may wait a little bit longer when it's moved around a bit this far into its orbit compared with the Earth, and it's more in the evening sky. As this goes on, that's called opposition. During this phase, when it's at its closest, then this peculiarity known as retrograde motion takes place. And this is the standard diagram, which is rather complicated, looks like a spider's web, showing the Earth moving around its orbit like that, and Mars over the same period, as you can see, going like that. And you trace these lines and they sort of cross over. Now, I wanted to do an animation of this, and I spent about an hour last night trying to put it together. Then I decided to look on the internet. And of course, there's this lovely one, which is on Wikipedia, done by someone who rejoices in the name of Frog23, of the whole thing going ahead. And you can see what happens as the Earth overtakes Mars on the inside orbit. So Mars appears to go backwards in its orbit. And that's a lovely demonstration there of the retrograde motion. It goes in a sort of loop, and because of the angles of the orbits of Earth and Mars are not in a flat plane as they are apparently on the diagram, then you see Mars go in a sort of loop in the sky. It doesn't go exactly backwards and then forwards again. It goes in a loop. So that's a nice demonstration of retrograde motion. Carrying on our explanation of opposition and the appearance of the outer planets, we're using Mars as the reference over an apparition. Incidentally, all the outer planets do go through retrograde motion as well. They all do those little loops in the sky, but Mars is the one with the most obvious and biggest loop. But the others do it as well. It's not just Mars. Then you get to a stage where Mars is now well into the evening sky, and at that point, at some point, it actually is getting quite low down and quite far from the Earth. But it's an interesting point. This is known as quadrature because it is when the angle between the Sun, Earth, and Mars is at its greatest. Now, this is when Mars shows its greatest phase. Normally, when it's opposite us in the sky, it shows no phase at all, just like a full moon in effect. Then as it moves around, it shows a bit more of a phase because the Sun is illuminating it more from the side. But then as Mars moves that way a bit and Earth moves that way a bit further, then we never see any more of a phase than that. Now, I've stolen one of Martin's pictures to show you the difference here, and that is Mars as it appears when it's at opposition or pretty well. And it's maybe a slight phase on one side. I'm not sure about the dates there for 2020. Actually, the opposition was on the 13th, wasn't it? So just a very slight phase there. But then back by the 23rd of January, you can see that Mars was showing a considerable phase there. Now, I don't want to dwell on this because Martin may be talking about that a bit more in his talk, but that this actually allows us to see a little bit of relief on the surface of Mars, and people taking images have actually shown the shadows of volcanoes on the surface of Mars. That's an amazing set of pictures for people who are suitably equipped. And finally, the planets, the outer planets, are only visible in the evening twilight. Now, Jupiter and Saturn are both getting to this stage at the moment, and they can stay quite a long time because the Earth is moving forward in its orbit. In the case of Mars, it's actually catching us up quite quickly. And so it stays there for a long time. Jupiter and Saturn move much more slowly, so they move more or less with the stars, but Mars can hang on for a long time. For example, the opposition was on 13th of October 2020, but the planet was into the evening sky until June 2021, and Martin was trying to follow it for as long as he could, and he managed to get pictures up until June. It was very tiny. It was a labour of love, really. You couldn't see much detail, but it could be done. And Mars hangs on for quite a long time. And that's a picture by Damien Peach showing the range of sizes that he was able to photograph. I'm not quite sure which was the first, probably that one there in the early morning sky. Then it got larger, and then at opposition it was like that. And then it started to get smaller. And usually when we see it in the evening sky and tend to photograph it, us lazy people, we tend to get it when it's not quite as large as it was at opposition. It gets smaller and smaller, and the phase increases. Here's a picture showing the three of the outer planets, Jupiter, Uranus, and Neptune. I couldn't get Saturn in the same shot, but it shows you the relative brightnesses of the three planets. Jupiter and Saturn, of course, in the sky at the moment. I'm sure you've all seen them. Mars has one opposition roughly every 2 years, as you know. But the giant planets, they move much more slowly because they're farther out in their orbits and have just one opposition per year. Jupiter moves roughly one constellation every year towards the east, while Saturn moves one constellation every 3 years, much more slow moving. And then Uranus takes a whole lifetime to move around the sky. Its period is 86 years, I think. And Neptune, I can't remember, 192, something like that. Nobody gets to see a full apparition of Neptune. But Uranus, if you are an avid observer and you start observing Uranus when you're about 8, you might just manage it. by the time you are reaching your dotage. And here indeed are the current positions. That view was taken incidentally in 1986. Do I mean 90? Yes. And you can see Jupiter was actually in Capricornus then. There's the Alpha and Beta Capricorni, quite a recognizable part of the sky if you see those two stars. And Jupiter was in Capricornus. Uranus and Neptune were also quite close in Capricornus. And now what's happened is that Jupiter is still in Capricornus, having moved twice around in its orbit, and Saturn is there. Of course, the two were close together last year, in about this time last year, and Neptune has moved not very far forward over 20 years, and Uranus has moved quite a bit more. So that shows you the movement of the outer planets in the sky. And the angle of the ecliptic has a lot to do with the appearance of the planets in the sky. And you can see this very well when the moon, and which of course both the moon and the planets are in the evening sky. And you can see that the sun has set down there, and the ecliptic in June is very, very low down in the evening. It skims the horizon more or less. And so any apparition of Venus that occurs in the summer months is going to be quite low down in the sky, and that's why we didn't see it so clearly this year. But if we move on to the next one, April, the spring, the angle of the ecliptic is very much more steep to the horizon, and you can play around with the sky mapping programs, and just it's well worth doing. Just put the ecliptic on the map and just flick from one day to the next over the months. You'll see that the angle of the ecliptic changes very much over the period of the year. So it's certainly not constant, and that has a lot to do with the affects the visibility of the planets, both the inner and the outer planets, very much so. Now, conjunctions, as I say, this is a much misused term. This is a true conjunction, Jupiter and Mars there, and as I said at the start, it is when the two bodies have the same, either the same right ascension as the Sun, or the same right ascension as each other. As in this case, Jupiter and Mars, they were closest together in very close together in December 1986, and that is a true conjunction. The actual moment of conjunction when they both have the same right ascension. And in the case of the planets, we often talk about the conjunction as being when there's a lot together in the sky. And this was referred to as a conjunction, 28th of April 2002. And there was another one back in 2001, where there were several planets in the sky together. We had Mercury, as you can see down in the lower right there, quite close to the horizon. Then we had Venus, then we had Saturn, then we had Mars, and we had Jupiter. And that was a really wonderful occasion where you could see all the planets in one go, and certainly all the bright planets. And that was quite a rare circumstance. I think it happened every, I can't remember how many years, but it's certainly not a regular occurrence at all. But last year we could actually see all the planets in the sky at one time, including Uranus and Neptune, and indeed Pluto, should you wanted to see it. But two of them, I think Mercury and Venus, were both in the early morning sky, and all the others were in the evening sky. So you can see the planets occasionally all in the sky at the same time, but usually you are limited to the visibility of the planets, just depending on where they are in their orbits. And we're fortunate that at the moment Jupiter and Saturn and Venus will be in the evening sky again over the next month or so, and Uranus and Neptune. Mars is in the morning sky, so we won't be able to observe that but in the evening. But this is often referred to as a conjunction, but there's only, for any two planets, there's only one moment of conjunction. And as you have more than one planet, then there are several different dates of conjunction between them when they both have, when the only two planets can be in conjunction at the same time. And this is the other definition of conjunction: when the planet has the same right ascension as the sun, and in this case Mars. You see the sun and Mars will have the same right ascension as each other at the same time. And the only time you actually see a conjunction, in the case of Mars there, you can see that it was behind the sun and therefore invisible to us. But in the case of a planet, this is another kind of conjunction when the planet has the same right ascension as the sun, and occasionally you can see it when the planet goes in front of the sun. This was 2004, and of course we had a couple of conjunctions like this recently. Mercury goes in front of the sun. We can see the Mercury at conjunction more often than we can Venus, but that's nevertheless a fairly rare opportunity to see a planet actually at conjunction. And this, let's see what the next one. This is one of the most spectacular sights that you can see in the sky when several planets are in conjunction at the same time, or near conjunction, as you can say there, particularly with the, as you can see there, with the moon as well. And the combination of several bright planets in the sky at the same time, as well as the moon, usually in the twilight sky, is something that arouses a lot of interest among people. It's also one of the things that you can photograph very easily, and when you get the right sort of circumstances, without too many telegraph poles and power lines and television aerials in the way, then you can get some really lovely photographs of the of what are really pulses rather than planetary conjunctions, which is when the planets have the same right ascension. So that's my quick run through different appearance of the planets. And at that point, I will invite you to ask any questions. I'll put my other earpiece in. I've got a message of chat here. Oh, yes. This is from, who's it from? John Murrell, a very good source of information. There are some, you can see a nice website there, youtube.com, and there's the link. Something that watched at lunchtime or after the meeting. I like the one showing the scaled rotation and axis of the planets. So there you are, that's in the chat at the moment. Now you're welcome to switch your videos on, and if you've got any questions or comments. Right, I'll take that as a no. Martin's here. Hi, Martin. Hi. I hope I didn't.
Hi.
Have you got you've got a comment, Martin?
No, it's quite interesting. You showing that comparison with Mars, showing the phase, which is, you know, can be really quite significant, and it causes problems in imaging when it's like that, because you get a much harder. So you get a diffuse side and you get a much harder side than you would normally get at opposition, and that much harder size then causes increased diffraction effects. So you often get this really quite pronounced, what's called edge rind effect, when Mars is close to quadrature and showing that you know, decidedly gibbous phase.
Yes, that's something I've noticed in a lot of pictures, and including my own, that you get these very sharp edges caused by over processing, really, isn't it?
Yeah, well, processing brings it out, but yeah, it's a diffraction effect, because you get you know, you've got a very hard edge there, really, and the processing brings that out.
Any other comments? I'm just going to get my my program up on the screen, which I haven't done so far. Oh, I'm using the wrong keyboard. Hang on.
Can I just say one thing, Robin?
Yeah, by all means.
The RAS spent 3 days the other day showing a live broadcast of Uranus, and that's now on on YouTube if anyone wants to see it.
Ah, right.
They were looking at, from the top of Hawaii at the infrared aurora of Uranus. But there's
did you observe that?
Well, they haven't
did you you watch that presumably? Tell us what you saw.
A lot of astronomers looking very bored in front of computers. But they put quite a few good interludes in as well. That's where I found those videos that I've just put the link to. But it's quite interesting, and you'd be interested to see if they do actually observe it. But
I did mean to put in a picture of Uranus actually at compared with Jupiter and Saturn, and I forgot to do that. So I can see if I can find it and show it to you. I'll have to switch shows at the moment.
I've got a background to keep Ian happy as well.
Yes, I noticed that you're in control of Jodrell Bank by the look of it.
I'm not sure about in control. I was allowed in the control room. Let's put it that way.
Oh, yes, that's one of yours, is it? Right.
Yes.
Okay.
I can't see that. I can just see Robin at the moment.
Oh, well, you need to change your view. I'm not sharing screen, so you should be able to. Everybody, please, by all means, maybe I've been.
Oh yes, there you are.
You can. Right.
I recognise who's in there actually, but I won't say. No, it doesn't matter. Apart from you.
Let me
That
see
was during the RAS meeting,
Very
the
good.
RAS visit, when we were allowed to ride on the telescope.
Very good. Not many people get anywhere near the place now, I promise you. Sadly.
Looks like I haven't copied the picture of the planets in the same scale to my to the right folder, so I'll have to find that later on and show you.
I think there's one on that link I just put on the chat, Robin.
Oh, right. Okay.
I think there's also a travel between them at real speed, at the speed of light, if you see what I mean, or real time. So it takes 5 hours to get to the outer planets.
Right. Yes. One of the talks I do aboard cruises is a tour of the solar system, and we go at 1 million miles an hour. And of course, we can get to the moon in a quarter of a second. We can get to the planets, the nearby planets, in just a few hours. But when it comes to the outer planets, it is extraordinary how long it takes to get to the. You go, even if when you want to go to the stars as well, you can't just go to 1 million miles an hour. You have to go to I forget what speed we choose, something like 1 million light years an hour or something like that. And even then, to go at you have to go many times the speed of light to get anywhere in a sensible speed in a sensible time. Even at the speed of light, of course, going to the stars takes 4 years to the nearest one. So you've got to go at some multiple of the speed of light, and even then, getting to the outer planets takes forever, as it were, more than the human lifetime, no matter how much you increase the speeds. And so, yes, the planets are. Space is a big place, as they say.
If anyone's in the southeast of England, there's a village called Otford in Kent, near the M25, M26 boundary or junction. And they've got a scale model of the solar system. I think it's 4 billion to 1. And obviously the inner planets are on a football field, but the outer ones, and it's still got Pluto on because it was a 2000 millennium project, is out in a field miles away. So if anyone's down there, go for a walk around it.
Well, actually, you can go a bit closer than that if you're in the London area, because at Ruislip Lido, as Martin knows, being members of the West of London Astronomical Society, and I'm just trying to find my pictures and can't. Ruislip Lido in West London also has a tour of the planets. As you walk into walk around the lake, the first thing you come across is a globe about 30 centimeters across, which represents the sun. It's up on the pole. Occasionally people shimmy up the pole and throw it into the water, which is not a good idea. And it doesn't burn up the whole of the reservoir. It's not that hot. And then as you walk along, you come to a display board, which shows you the details of the planets and the planet to scale. And it was quite educational to do that, because with the sun that size, the size of the Earth and Mars is absolutely minute. And on the display boards, it's literally just about the size of a pea for the Earth and that sort of thing. And even Jupiter and Saturn are only about the size of an orange. And you've got quite a walk to get to them. And if you really want to go to Neptune, then you've got to walk around the whole of the reservoir right at Lido. It's quite a trek, and that's still there.
Yes, Oxford's much the same, I think, but they've built them out of stainless steel as they're being a bit more vandal-proof.
That's a red rag to a bull to really vandalise. Okay,
I
right.
mean, so interestingly, with those sort of scale models, if you scale the diameter and the distance, then when you stand at the position of the Earth and you look at the other planets, they should be the same angular size as the sky.
No, I did that for a public weekend where I actually got little images of all the planets, put them on cards at the right distance, and then put a telescope at the Earth. And of course, they look the right size.
Yeah, exactly. Yeah, quite interesting.
Steve's got his hand up. Steve Knight has got his hand up. Can you unmute and ask your question, or go on video, Steve? Or was that an accident that you've got your hand up? Oh, there he is. Look, can't hear you. You're still muted.
Yep.
That's it. You got it.
Sorry about that. Great talk, Robin.
Thank you.
It was interesting seeing that image that Damien took, showing the relative sizes of Mars as it approaches opposition. I'm just conscious that you see some people talking about the date of the opposition of Jupiter and Saturn, and if the opposition was a month earlier, they feel like they've missed the opportunity to look at it or take pictures. And of course, for the outer planets, the relative size difference of around opposition is a very, very shallow curve. So the difference in angular size is very, very little.
That's right. And you leave it too late. We did this for National Astronomy Week last year. We realized that although the opposition was on the 13th of October, and that would have been a good time for National Astronomy Week, being milder and all that sort of thing. The problem was that it was also still British summertime in force, and the planet was at its highest. It wasn't all that high at 1 a.m. And so we thought, well, that's not the best time to get people out there observing it. And that was before we planned that before COVID came along. And so in the end, we went for about a month later in November, but at least the planet was more observable then. You're absolutely right.
Yeah, I remember I plotted a curve of the angular size of Jupiter in reality, and then the angular size according to social media, and it's sort of flat, and then it peaks at opposition, and it goes down. And it's people miss an opportunity if they think they're too late to image them or too early. They should be looking at them all the time.
Absolutely, yes. And well, Martin, will you be showing your sequence, Martin, of Mars this time over the apparition? You've taken some. We've published some good pictures in Popular Astronomy of yours over the apparition.
Yeah, I mean, I hadn't planned to. I hadn't got that montage. No. Not enough time really. But I think the comparison that you showed there between how it appeared in January and how it appeared at opposition was quite good.
Okay, well, we're going to take a break. I'm going to take a break now. Just get a glass of water or something. So I'll leave you with the backdrop. It may morph into a blue screen, but the next talk is on in just 4 minutes time. So Ian is going to get ready. So if Ian is going to be talking about telescopes for planetary observing. So while I go and get a cup of tea, now let's see. I need to allow Ian. Let me just check the sharing options here, because this could go wrong. Who can share?
I can't at the moment, Robin.
No. Okay. Right. Well, what I'm going to do is make you the host, and then you should be able to share. I fear what would happen if I allowed everybody to share the screen because it could be a problem. So you're now
co-host is better in case I can't get back to you at the end.
Well, I didn't have that option. It's a meeting, not a webinar. So you're now the host, so you can share your screen.
Well, I try.
So I'm going to stop my video and hand over to you.
Well, can everybody see that? Someone let me know.
Yes, I can see it.
Okay, well, we've got a break. Just have a few minutes if you want to, and then I'll begin. It's a good start. I'll wait till 5:02, the nominal time. It's good to see we've got quite a few more people now. It's around 50, I think, if not more. Excellent. Well done.
Ian, while we're waiting, I've got a bit of a bone to pick with you. I went to a talk you gave. I think it was a joint talk between one of the National Photographic Societies and the British Astronomical Society. Must have been about 10 years ago. And you got me into this, so I hold you personally responsible for the thousands of pounds I've spent over the last decade.
Oh dear, well, I don't feel too bad about that. So I hope you've enjoyed the expenditure. What you've bought, that's the important thing.
I have indeed, yeah, great hobby.
Jolly good. I hate to think how much I've spent over the years.
I bet.
I've only ever bought 2 telescopes new. Virtually everything has come from UK Astro Buy Sell, if people know that.
Yeah.
And usually somewhere between 50% and 70% of the new price. And I've got some lovely telescopes that way. Some of them at quite ridiculous prices. So that's how I built up my collection. I think we've got about 30 seconds to go, according to my watch. Well, I guess it's about time. So good morning, everybody. I've slightly extended the title because you're going to get 2 talks this afternoon about imaging the planets, the most important one being from Martin, but I'll be giving one about the types of cameras you might want to use. So it's telescopes for planetary observing and imaging. So let's have a go. The first thing to point out, of course, is that planets have very small angular sizes. And those are basically the values we get. Those of Uranus and Neptune virtually change, hardly change. Mars at opposition can change by a factor of 2. And of course, it was in 2003, we had this wonderful closest approach for 60,000 years, which I'll come to at the end of the talk, actually. Saturn up to 18 arc seconds, Jupiter up to 49, which is wonderful. And Venus, of course, varies quite widely as it comes around the sun. And that does tend to mean that to observe planets, you need to have telescopes with relatively long focal lengths to get a large enough image to see easily without having to use too high power an eyepiece, and these are never very good. So that's what I've just said. One needs to have a telescope with a long focal length, hopefully anyway, but also, of course, the resolution of a telescope can also play a part in what we call the seeing is good. And I'll be discussing seeing in much more detail this afternoon. So what about resolution? Well, essentially, if you had a perfect unobstructed aperture, like a refractor, and I do love refractors, you have an image of a point source, like a star, gives you, first of all, an airy disk, which has about 82% of all the energy in it, so that's the brightest bit, but that's then surrounded by what are called diffraction rings, and you can see them there. And the diffraction rings are a good bit lower, but overall, they add up to a reasonable amount. And depending upon the aperture of the telescope, oh, that's just a nice little 3D view it does show you that that first ring isn't really all that much to worry about. So there we go. And these are what you typically get if you go on the web and look for the resolutions of telescopes. 4-inch, 1.4, 6-inch, 1 arc second, 8, 0.7, 12, 0.5. So you might think that if you use a 12-inch telescope, you'll get a wonderful resolution of half an arc second, which would mean that when Jupiter was getting on for 50 arc seconds across, you'd have 100 pixels across it, and you'd see very well. Trouble is, as we shall see, the atmosphere has a major role in what we can actually see. Now, this is something that a lot of people get the wrong end of the stick, I think. I've heard people say you can't use a Smith-Cassegrain because the size of its secondary mirror reduces its contrast. Well, I don't really believe that anyway, but the point is this. It is very important for visual observing because planets tend to have rather low contrast features, particularly Saturn. The bands on Saturn are not terribly obvious. It's not quite so important for imaging because, in fact, we can up the contrast of an image in what we call our post-processing. But there are two aspects on image contrast, and not many people split them up. The first one of these is overall contrast, and that's where light can fall anywhere across the image from where it shouldn't do. And then there's micro contrast, which is where light is deflected from where it should be by a matter of arc seconds. So that's why it's called micro contrast. Let me talk about overall contrast first. So it's reduced by the scattering of light within the objective of a refractor or at the surface of a mirror, and also, I suppose, in the corrector plate of telescopes that use them. Now, think about this. If you look at possibly when you're trying to collimate a Newtonian with a laser, you look down in the screen and you look down into the tube and you can actually see the red light of the laser on the mirror. You're trying to make it move into the center usually a little circle on the mirror. The fact you can see that means that light is being scattered. And also a certain amount, as we'll see, is scattered within the objective of a refractor. And then you can also have off-axis light coming onto the eyepiece or camera sensor. And particularly, of course, if there's moonlight around, that's a problem. That can be reduced by good baffling in the tube assembly. And so overall contrast affects the whole image. Now, refractors have the highest overall contrast of any telescope type. The glass objective perhaps scatters about 2% of the light, which is not very much. And if you have a well-baffled tube, very little extraneous light will actually fall on your eyepiece, so you observe it, or on your sensor. And that's just to show you, some nature photographers are actually using little ED refractors. And I took this picture of a swan with a little 80mm Williams Optics ED refractor. And I think you'll agree the contrast is very high. That front covered a magazine some time ago. So refractors have the highest overall contrast of any telescope type, which is one reason why I love them. Now, the other thing is microcontrast, where you have diffraction from secondary mirrors and spiders, which shifts light away from the airy disk, either into the first ring and a bit beyond, but also the spider can produce spikes around bright stars. Now, they're very pretty. And when you're taking pictures of stars and things, it's nice. But if you're trying to image, say, Jupiter, then it does make some light shift from where it should be to where it shouldn't. And that's, again, the effect I'm trying to show on the right-hand side in that plot of what happens as you increase the obstruction. So without, you see the red line. As you increase the obstruction to 20%, the blue line, and then 33%, which is a typical Smith-Cassegrain, the green line. And it doesn't quite have as much effect as you might think in some respects, perhaps more so for viewing than for imaging. But that's what does happen. Now, refractors do not have a secondary obstruction, so they show the best micro contrast. Anyway, now let's have a look at some of the telescope types. I think I'll be through this in about 10 minutes. I hope it's a bit longer than that. First of all, refractors. And I saw the word on Sky and Telescope magazine called refractophile. And I have to say I'm a refractophile. I think I've got 7 of them, ranging from 66 millimeters aperture to 150. That one actually is only an achromat, which I got very cheaply because I wanted to buy the mount it was on. I wasn't so fussed about the refractor, but it still does work. Well, I'm sure you know that the first use of what was called a spyglass originally was by Galileo Galilei. And the great thing was he optimized the design. He didn't just take a standard little convex lens. He tried all the various shapes, and I hope you can see them up the top. Some things get covered up on the screen. But if you had a convex lens with a certain power, it could have various shapes. I hope you can see them. It could be a plano-convex, one way or the other. It could be equally curved faces on either side, or so on. And basically, the one that he chose, you can actually see the shape of it in that diagram on the left there. I can point to it, I think there, is here, which is where you have the minimum amount of what they call spherochromatism. Anyway, so basically, he had the best possible single lens objective that you could possibly have. And because of chromatic aberration, we're going to talk about that, you have to have a very long tube relative to the aperture of the telescope. And these were telescopes that I began to make with cardboard tubes when I was about 12. I had to wear pretty thick glasses then. And the optician in our village, quite why a little village had an optician, I don't now know, but he was a great friend, Jimmy James, of my father. And he gave me lenses, thin lenses for the objective and thicker ones for the eyepiece, just 2 lenses. And I made telescopes, and I could see the craters on the moon a bit, and I think the moons of Jupiter. And I was lucky enough, I lived only about 100 yards from the south coast at a village called Feltham, not far from Selsey Bill, where I think Damien Peach might live now. And so that got me into astronomy. And just a matter of interest, these are some drawings or etchings that were made by Galileo, or people who worked with him. And the thing I'd point out is, over here, do you see sort of Mickey Mouse upside down, the 2 ears, the head, and the body? And that's actually Mari Quisin, you might know. And just for comparison, those are 2 photographs I've taken of the moon at the 2 phases, almost first and third quarter. And I think you can see Mickey Mouse quite nicely over here. I'm not a very good planetary imager, but I'm a competent, I think, lunar imager. Okay, well, the single lens gives rise to a fair bit of chromatic aberration, and that's just shown vaguely in the image down to the left. A chap called Chester Hall Moore in the 1700s realized that if he put a piece of ground glass adjacent to a piece of flint glass, he could make what is now called an achromatic doublet, and that significantly reduced the chromatic aberration. And if you have a telescope which has got a fairly long focal ratio, say f10 to f12, they can actually work very well. A bit of interest about this. He wanted to keep his invention secret, so he contracted the making of the crown glass element and the flint glass element to 2 different opticians. But they both subcontracted those lenses to a 3rd optician, who realized what was going on, and he began to make the odd little achromat doublet himself. Later on, he told John Dolland about it, and he got a patent in 1758, I think it was. I think that might be the Dolland of Dolland and Atkinson's. So there was a bit of interest in it in its history. Well, what do we tend to find if we try and go and buy a refractor? The majority are from 60 millimeters to 150. They get very big and unwieldy beyond 150, but people do buy them. And you can spend over £10,000 in getting something like a 180 millimeter Apo refractor. Focal lengths typically from 350 to 1,200 millimeters. And then the focal ratio is typically from f5 to f10. f5 is pushing it a bit. f6 now with the latest optics is okay. And with f10, you can, with the latest lenses, have virtually zero chromatic aberration. You can make some wonderful planetary imaging refractors. And this is my bestest telescope. It costs an awful lot now than when I bought it, because I bought it before the company were not well known. I think it's doubled in price now. It's a forgive me, this is an f10 achromat, and that actually can work pretty well. So if anyone's a young budding astronomer, then I would certainly say have a go and get it one of those. They're not too expensive, and you'll see an awful lot with them. Now, you get less chromatic aberration if you use one element of what's called extra dispersive glass, ED glass. And you'll find that many camera lenses say they're ED. There's a whole range of glass types, but also there's something called fluorite crystals, CAF2, from which you can make lenses. Terminology. Achromats bring two colors to the same focus. Apochromats, they bring three colors to the same focus, so they have very low chromatic aberration. And then there are things we call semi-apochromats, which use ED glass to reduce the chromatic aberration of an achromat. And to be perfectly honest, many of these are called apochromats, although they're not really true apochromats, but they do work very well. Typically, one of these semi-apochromats will show some false color around the image of, say, Venus or a star when they're out of focus, but should not show much when they're in focus. Whereas a true apochromat probably will give you clean images both in and outside of focus. And there are various crystal types. I don't want to spend too much on this, but Ohara in Japan make quite a lot of these. They start off with the FPL, and then they have 51, 52, 53, and 55. Now, up to very recently, FPL 53 was one of the best of these. Notice at the top there, fluorite crystal has an Abbe number, 94.99. That sort of defines a dispersion. And you can see that FPL 53 is almost the same. So some people call it an FD lens rather than an ED lens, and that's a fair comment. And I've got a couple of refractors which have got these FD doublets in them. I make the point about FPL 55 because that seems to be replacing FPL 53. It's pretty close. It's easier to work with and probably cheaper. And I have begun to find some refractors which are advertised saying they're FPL 55 rather than say 52 or 53. So you might spot that. They're going to be very, very good. And I'll come back to the fluorite crystal very shortly. I should just say that the mating element used to match the characteristics of the ED element are just as important. And in fact, FPL 55 works very well with some relatively cheap crown type lens elements. So that's another reason why it's becoming into use. And I don't know if you can see this on the web, but that was a picture I took with an achromat, and on the right with a semi-apo, an FPL 53, essentially no chromatic aberration on the right image. I think you can see a hint of the sort of purple color. And that's because an achromat, they generally try and make it best to work for visual observing. And that means that the sort of the red and the blue ends of the spectrum, which the eye isn't so sensitive at, basically come through a bit. And a bit of interest, I have had 2 cataracts replaced. Before I did some tests when I was taking these photographs, looking at the moon with both the achromat, it's actually a guide scope telescope I have, 80mm, and I could see no false color at all. Essentially, the cataract in the eye was actually cutting out the red and the blue parts of the spectrum. When I had one eye fixed and the other one was normal, with the fixed eye, a white wall was white. With my uncorrected eye, it was yellow. So they were acting as a yellow filter and reducing the chromatic aberration. a fluorite doublet has a better correction than the ED doublet. Can you see that green line? That's in fact what you get. It says FS102, which is a Takahashi 4-inch telescope. It's one of my prized possessions. It was the first telescope of any note I ever bought around 2020, sorry, 2000, the turn of the millennium, shall we say. And that does actually mean you get rather less chromatic aberration. And that's in fact the one I've got, an FS102. But there's something else which is quite important about fluorite. Fluorite doublets do not scatter light. If you shine a laser beam through the objective of your telescope, if it's got 2 or 3 glass elements, you'll actually see the passage of the light that's going through. Each of the elements might scatter 1 or 2% of the light. But if you shine it through a fluorite doublet, you do not see any scattering from the fluorite. That means the contrast of a fluorite doublet is the highest of any possible telescope you can make. And at a lovely Isle of Wight star party quite some time ago now, I took 2 photographs of the 40-hour-old moon. The one on the left was exposed correctly for the limb of the moon. You can just see some of the craters there a bit. And then I increased the exposure substantially so I could see the earth shine. That's the light that's been reflected from clouds on the earth. And you can see that there's very little of the light from the very, very bright part, which of course was very bright when I actually took that second image, to actually spread over the actual earth shine. And in fact, I do not believe you can take a better picture of earth shine than that one on the right, because you cannot get a better telescope to do it than a fluorite doublet. You can now get triplet objectives. They cost a bit more. There are 2 basic types. They can be air-spaced, and I do have one of those. That actually is easier to design, but there is a bit of a problem. It's quite hard for the central element to lose heat if you take it out into a cold night. And that's because there's an air gap between it and the elements on either side. It makes it hard to cool down. And it is said that if a night is cooling down quickly, a triplet objective may never actually come to equilibrium. But if they are in equilibrium, you actually get apochromatic effects, results, and so the chromatic aberration is very, very much reduced. And that's compared to a doublet on the top right. You can just see what happens over on the left. Now, on the other hand, 1 or 2 manufacturers oil space their triplets. The first thing, of course, about that is it means that the inner element can lose its heat much more quickly, so that's good. And I do have one of those. And Tech, a wonderful American company, they're now oil spacing their triplets. And incidentally, they're using a fluorite element now. Fluorite went out of sort of use, really. Takahashi stopped using them, but they're beginning to come back. And that is quite interesting, I find. And the other thing is, they're actually easier to make. If you think about it, as you've got oil between the central element and the 2 outer ones, the surfaces don't have to be too precise. If you put oil on the surface of a rough piece of something or other, or water, it basically effectively removes the effects of all the little imperfections. They're slightly harder to design. And in fact, the one I've got has to have some aspheric surfaces just to make it as good as you could get with an airspace one. But nevertheless, a lot of these are around now. Telescopes of very high quality are becoming far, far cheaper than they used to, particularly in the realm of refractors. And this is in fact my bestest one. I'm sorry I got there too early. A 127mm apochromat. It's an oil-spaced f7 objective. So it's not trying to push the focal length too little. And it has a focal length of 900mm. Now, for imaging or observing, particularly, or both, the planets, the image scale is a bit small. But if you add a Barlow, or in my case, I've got a 2.5 times TeleVue PowerMate, which works a bit better than the Barlow, it is said, I get a focal length of 2200, which is actually pretty good for planetary observing. And that's probably the best telescope I've got for actually visually observing the planets. It may not be the best for imaging, but it's probably the best I have for imaging. So, refractor conclusion, a longer focal length refractor can give wonderful views of the planets, given that you have a Barlow lens or power mate to increase the effective focal length. If the seeing's not good, they will cut through turbulence better than larger aperture telescopes. More of that this afternoon. And this is not what I've said, but someone who I think has got 10 refractors amongst a vast number of telescopes, he's on the web, he says a 4-inch refractor will show you about 90% of what one could see in principle on most nights of good seeing. A 5-inch refractor, as I have, will show you pretty much 100%. So what about Newtonians? Well, you all know they were invented by Isaac Newton, who wasn't a very nice guy by all accounts. That's a model of his first one. You have a secondary mirror to reflect the light sideways to the eyepiece, because if you didn't have one, your head would be in the way. That secondary mirror is an obstruction, and that, as you saw perhaps earlier, deflects some of the light from the central part of the airy disk out into the ring. So it reduces the resolution to some extent. So that's what I've said there. It reduces what we call the micro contrast of the image. Now, if you have a very low profile focuser, so the eyepiece is very, very close to the tube, the secondary mirror does not have to be as big, and that's good. But also, if you reduce the size of the mirror, you get a problem called vignetting. The outer parts of the image you might be observing with a 1 1/4, 35, 32 millimeter eyepiece or something like that will not be as bright as it should be as compared to the center. That's a problem. So for wide field observing, you need to have a large secondary mirror, and imaging is more important perhaps even. But you can see if you're observing a planet, hopefully you've got it in the center of the field of view. You only really need to have the full brightness that your 6-8-inch mirror could give you at the very center of the field of view. And that means you can significantly reduce the size of the secondary mirror. So you can optimize a Newtonian for planetary imaging by using a small secondary mirror. In fact, some telescopes can be bought with a pair of secondary mirrors, one for wide field and one for the use with planets. And one can always change them if you wanted to. Longish focal length ratios are far better for this than short ones, f8 to f10. An 8-inch f10 optimized Newtonian, that's with a very small secondary mirror, would provide perhaps the very best planetary scope you could have. And it wouldn't actually be all that expensive. Newtonians give you the best capturing ability of any telescopes for the money. A type that doesn't seem to be very popular these days is a Cassegrain telescope. It just uses 2 mirrors, one of which is not is shaped away from what we might have as a parabolic mirror, which we have in Newtonian. Stella Lyra is a range sold by First Light Optics, and they will sell you an 8-inch f12 Cassegrain for around £949. And look at the focal length. Their f12 is 2,436 millimeters. So that actually would make it a very good planetary either imaging or visual. So that's not a bad telescope to have. I would just warn you that Cassegrains, and I actually have a Ritchie Cassegrain, are quite tricky to collimate, much harder than either Newtonians or Smith Cassegrains that we're going to get to. You can buy a 10-inch truss tube one if you really want to look like a professional astronomer, and that one has got a 3,000 millimeter focal length. So it gives you pretty good image sizes for your planets, and that's a mere just under £3,000. I have to say that until a company called GSO Optical in Taiwan started making these, you'd probably be paying about £15,000 for a telescope like that. So then we come to perhaps the most popular telescopes of all, catadioptrics they're called. It's a funny word, that, don't know why, but it uses mirrors. They use mirrors and lenses. And I've got quite a few of these, I'm afraid. This is one, it's a Mac Newtonian that I actually picked up for £200 at the Equinox Star Party. It was in a sort of almost a junk box that Telescope House had, and they cost over £1,000. So I say I have picked up telescopes really quite cheaply. Now you can see that it has a corrector plate. The main mirror is spherical, and that's corrected by this curved, quite thickly curved meniscus lens at the front. It does have, as you can perhaps see, a very low profile focuser, and the secondary is not that large. And that's another look at it. I think it may be the same one, but you can see how small the secondary mirror is. It's really optimized for observing the planets, and I've had some lovely views of both the moon and the planets with it. Now, I'm afraid they're not cheap, but they do work very, very well. And that's just a view of part of the moon. I love this phase of the moon when the terminator cuts across Sinus Iridum, the Bay of Rainbows, and the edge of the original crater here stands up against the blackness. And you can see Plato here, and that's the Alpine Valley, the Apennines, and of course Copernicus. It's a lovely part of the moon to look at. Oh, and also Mons Piton here. You can just see a shadow, and when I was teaching, I used to get the students to calculate the height of the mountain determined by the length of its shadow. And that's actually quite a complicated calculation because you have to work out the angle of the sun, and that's not too easy. So a Schmidt cassegrain. Well, again, that has a primary mirror. It has a rather interestingly shaped corrector plate. And it was when the guy who started off Celestron found out that there was a cheap way, an easy way to make a corrector plate, that these really came in. They were very expensive to start with, but now they are very cost effective. One problem I'll come to is, of course, the corrector plate can be dewed. But apart from that, they're pretty good telescopes. There are one or two things about them I'll come to shortly. Meade and Celestron both make them, and they make two versions. The standard ones come with 8, 10, 12, 14, and even 16-inch sizes. I have looked through a 16-inch Meade from observatory in the Isle of Man under perfect transparent skies following very, very heavy rain. And we could all see a lovely iridescent green color at the heart of the Dumbbell Nebula. It's one of the very few times I've ever seen any color with my eyes. Celestron go up to 14 inches. We'll come back to 14-inch ones a bit later on. They have all about f10 focal ratio. They're focused by moving the primary mirror. And that can be a problem when imaging, because when you twiddle the focus, it gives what's called some image shift. And if you have a very small sensor, as you might do, as we'll see, it can actually move, say, Jupiter out of the field of view. But you can do, and I have done, is I've added an external focuser. So instead of just putting a right angle diagonal at the back, I remove that and I put on a focuser. This is the one that I have, and I mention it for a couple of reasons for later. It's the 9.25-inch one. It's a slightly longer tube because it uses only an f2.3 primary rather than f2, which is a bit easier to make. It makes it longer. You have a slightly wider, flatter field of view than you do, say, with an 8-inch or even the 11. And some people say it's the SCT, Schmidt-Cassegrain telescope, for those who do not like them. Anyway, they're very nice telescopes, and we'll see some pictures taken by them a bit later on. There's an incorrect statement. It says that Schmidt-Cassegrains are not good for planetary observing, as due to their large secondary mirror, they have low contrast. And that really is not true. This large secondary mirror does actually give you a little bit of micro contrast reduction. That can be got rid of, certainly, when you're doing photography, which I think Martin will tell us about later on. But nevertheless, it's not as bad as you might think. And I've had some lovely views of Jupiter with my 9¼ And these are two Damien Peach images when he was using a 9¼ Now he's obviously gone up market now because he's using 14-inch ones, but nevertheless, it does show you what you can do with a Schmidt-Cassegrain telescope. So they should not be denigrated. You can see the lovely divisions here, Cassini's division, and there, this is called Encke's division. It's so thin that no one can understand how Encke could see it. But anyway, it's called after him. Now, okay, that central obstruction reduces the image quality to some extent. It moves light away from the central part of the disk out into the ring. But this is a diagram produced by Damien, I might say. It shows you the effect as you go from very fine details, that's where naught is, up to very large scale details. A perfect 9.25 aperture would have that blue line there. That's as good as you could get. An actual 9.25 Schmidt-Cassegrain gives you that red line. You can see for wide scale images, it's no different from perfect. It's not as good as it would be at fine detail, but look, it is hardly any worse than a perfect 6-inch unobstructed aperture. And no one says the 6-inch unobstructed aperture refractor is no good for planetary observing. So take that image and just remember that these relatively large Schmidt-Cassegrains can actually be very, very good. Meade make their advanced coma field telescopes. F8, slightly different. They're 8 to 16-inch. They use hyperbolic secondary and an altered corrector plate. They didn't initially call them Ritchie-Crescent, but the firm that made really good Ritchie-Crescents at the time took them to court. So now they call them ACF telescopes. The great thing is there's no coma, and that's a problem that you have towards the edges of a wide field using a Schmidt-Cassegrain. Now, of course, that's no problem if you're imaging or observing the planets, but it would be better if you're trying to do wide field imaging or observing. And Celestron have their Edge HD, which works in a similar way, but in this case, the correction is done by having a couple of elements in here. And I, in fact, have a Vixen VC200L, which in fact does not have a corrector plate. It has a correcting lens here. The light goes through it twice, and again has some lenses in here. And that's actually one of my bestest telescopes in terms of something which is a catadioptric. So you don't need these for planetary imaging or observing, but they are better, but a lot more expensive for wide field imaging. That's what I've just said here. We now come to Maksutovs. A Russian, Gregory Maksutov, didn't have the ability to make one of these rather specialized corrector plates. And he worked out that if you used a much thicker meniscus plate and the radius of curvature, they're both spherical on the front and the rear, they're different, you could actually get correction as well. And the majority of these, they're called Gregory Maksutovs, have the secondary mirror basically illuminized on the inner side of the corrector plate. And you can get lots and lots of these around. They do make very, very good planetary imaging telescopes and viewing ones. Their focal lengths are quite long because they're f12 to f15. Skywatcher makes some wonderful ones, 102 to 180 millimeter apertures. And that's a picture of the SkyMax 1/8. A friend of mine has got one and does wonderful things with it. And I don't have, I think, here 2 pictures of his. That's the lunar one, that's Mare Crisium, and that's really very, very good indeed. And over here, we have an image he took just a few nights ago of Jupiter. Obviously, Jupiter is very low in the sky at the moment, but next year it will get higher. I've been having a go myself, no better than that image, when it's been about 24 degrees elevation when crossing the meridian. But happily, I went on Stellarium to look what it would be like at opposition next year. It's more like 37 degrees. So it'll be a lot better to view an image next year. Let's look forward to that. So these Maksutovs are very good planetary scopes. The Rumac is a separate type. I think it was designed by someone called Rutten, and it has a secondary mirror, which is not illuminized, it's actually mounted on the back. That means it can have different shape. That gives the optical designer some degrees of freedom. And I do happen to have one of those, which is F10 127mm one, which is a lovely scope. Again, I actually got that for £200 at an Astrofest, being sold by someone who wasn't there by his his astronomy society. And I felt slightly bad about buying it because that particular telescope now costs just over £1,000, which is ridiculous. They're Russian, built like a tank. And I think somebody said they were used by tanks as finder scopes or something like that. And this perhaps would be the ultimate of these. Orion Optics, they were in Crewe, they're now in Stoke-on-Trent. I've known them for many, many years. I've got two of their telescopes, actually, an 8-inch Newtonian. Incidentally, they produced many years ago what they call their Hilux coating. And these are multiple layer coatings that go on to the mirror. They increase the reflectivity, but more important than that, they prevent moisture getting at the mirror surface. And I bought that, I think, in the year 2000, and that mirror still looks almost like new. Anyway, if you've got 6,400 to spare, you can get one of their Maksutovs. It only has a 22% diameter secondary obstruction, and that must be a very, very good planetary imaging telescope. Not that I think I could afford one. Now, this is a problem. Tube currents. If you take a telescope out to the outside, obviously it's got to acclimatize. If it's actually got a closed tube, like a Smith-Cassegrain, the air to some extent is trapped inside. And you can actually buy little fan things that you stick through the eyepiece to blow cool air into the inside. But notice, in a refractor, the light only travels down the tube once. In the Newtonian, it's twice. In a Cassegrain and others like that, the Maksutov, it's 3 times. So it's more important that they actually come to acclimatization. So you've got to allow time for the telescope to cool down. If I think it's going to be clear, you know, about 4 o'clock, I look on the weather forecast. I will actually take the telescope out I'm going to use and basically set it somewhere nice so it can acclimatize. I do, in fact, have a mount permanently in the center of my garden. And so I just literally have to put the electronics on it because it has an external control system, which is very nice because I can bring that in. The electronics can be brought in so they don't stay out in the cold. And I just have to sort of put the power and things on and add the telescope. So that's not too long. So I take them out to cool down in plenty of time. And one thing you see, actually, little bubbles in your star image you see on the left, but also you see what's sometimes called bleeding. You can see it there, obviously going the wrong way up because I suppose the telescope is inverting the image, and that's the effect of tube currents. And again, if you have, as I mentioned, a Smith-Cassegrain or a Maksutov, they're very prone to dewing. And I must admit, I took my 9 1/4 out not that long ago, and I hadn't really set myself up with dew shield. I had a dew shield, of course, but not a dew heater band. And I was actually having to use a hairdryer just to get the dew off it about every 5 or 10 minutes. I mean, it was a night. Everything was dripping with water. The problem with the dew heater bands is they do really need some current. Okay, if you've perhaps got some mains, but do be careful with mains. Have one of these earth leakage trips before you bring your cable out to the telescope area. If you're out in the field, then you need a fairly hefty battery to actually power them overnight. And these are the sort of things you can get. I've got that Celestron dew shield up on the left. You can buy them from AstroZap, which have a built-in dew heater. You can see one of these little bands on the left. I've got a couple of those for my telescopes. You can also get them. Can you see the for a finder scope. And I have to say that that night, my finder got totally dewed up as well. Of course, to have these, you tend to need to have a dew controller, and they can cost about £50 to control the current going into the dew band to control its temperature. Focuses are quite important. One thing that's happened over the last 5–10 years, whereas nearly all refractors and many other telescopes were provided with what are called, oh dear, my brain's going, doesn't matter. Anyway, focuses which had little rollers that moved up and down, they are not so good when you try and have telescopes. My brain's going, I'm sorry. When you have cameras attached to them. And so now many telescopes are being supplied with what are called helical track focuses. You can see the helical track there, and they can cope with much greater weights. You can obviously lock them, but they tend to be the right thing to have. Another type, which is not quite as good, but not so bad, is called a steel track focuser. And there, they actually have a steel track on which the rollers run, and that's a little bit better. So that's not a bad thing to have. A Schmidt Cassegrain is basically focused by adjusting the position of the primary mirror, and that can cause a little bit of focus shift, which can be a pain when you're planetary imaging. It's a fairly coarse control. You can buy these little micro controllers for it with a 10-to-1 reduction. They're relatively expensive. As I said earlier, it's much better to actually put on the back a type of focuser, helical, otherwise. It doesn't have to have much of a length of draw tube, because you do the main focusing using the focuser on the primary mirror, and have, when you do that, this little focuser here, and it's mid-travel. And then you can make very easy fine corrections just using the little ×10 focuser control. So that's quite good. And I should have said the type that we had a lot, there were Crayford focuses, and I forgot that. Anyway, Crayford focuses are now tending to be replaced by either steel track or even better, helical track. I was meant to say a little bit about telescope mounts fairly quickly. They can either be altaz or equatorial. If you're certainly doing photography, you have to downrate their carrying capacity by at least a third from what they say in the specs. You should probably spend a fair bit more than the telescope on the mount. And that's particularly true if you're trying to do imaging. You've got to keep the planet centered on a tiny sensor. And you've got to have a reasonably good and sturdy mount for that can do it. Altaz mounts are perfect for visual observing and much easier to set up. They do suffer from frame rotation if you're imaging, but that's probably not a problem for short video sequences. And they're fine for DSO imaging, where you might think they're no good. You have to actually have sequences of images not too long, and then you may slightly rotate the camera between them. And something like Deep Sky Stacker corrects for the frame rotation. And this is one that I'd love to have. I would buy it for the fact that I've actually got the smaller version, which I've had, I think the very first one that was imported some years ago. It's called the Altron AsMount Pro, and it has a built-in lithium battery, and I would commend that to anybody. It really is good. Equatorial mounts, they're to some extent better for imaging because you don't have to worry about frame rotation. One of the nicest of these at a reasonable price is a modified Skywatcher HEQ5 Pro, and that has got a belt drive that makes the tracking rather more smoother. And you can actually buy these ready modified, and that's a picture of one sold, I think, by one of, I think it was Rother Valley Optics, I suspect. And finally, a tale of two scopes. When Mars was closest to the Earth in 2003, in August, and that's important, we had a lovely star party at Jodrell Bank. There were probably 20 telescopes there. The Discovery Centre, as it is now, the Visitor Centre, had a big concrete patio out of its front on the right side to view Mars. And that's where everyone had put their scopes. Now, I may have arrived late, and another lady arrived late, and we put our scopes on the grass towards Mars. She had just bought, I think it was only about £250 then, an 8-inch Skywatcher Dobsonian, as the one you see there. And I'd actually only just recently bought my Takahashi 4-inch telescope. So now the current costs are higher than they were then, but I think my system on a reasonable mount would cost 3,000 and the Skywatcher is 369. We obviously spent some time going around looking through everyone's telescopes. And I promise you, the consensus was that hers and mine gave the best images. Some people thought mine did, but I actually thought that the image through her Skywatcher was better. Now, why was this? Well, I said it was August. During the day, that concrete patio had warmed up. So all of those telescopes mounted there were looking through turbulent air. And of course, anytime you're observing, try not to look over houses. I've seen Jupiter through the outlet of a chimney. I mean, it was incredible. So be careful where you mount your telescopes. That's quite important. And that's why theirs were not so good, because some of those telescopes were up to £5,000. That's one thing. But the thing I really want to say to end this little talk is that you can get exquisite views of the heavens without having to spend too much money. And that's the talk I was telling you about. That's the time when Mars was closest, August the 25th, 2003. So the lessons can come from that tale, as I've said. Make sure your scopes cool down, well collimated. Make sure where you sight it. And most importantly, you do not have to spend large amounts of money. So there we go. So I'll stop sharing. And we may just have a little bit of time for questions.
Great.
Now,
thank you very much, Ian. That was absolutely super. And I'm sure everyone learned a lot there. As I've being at Preston Montford, I've heard your talk a few times, but I always learn something that you've added or I've forgotten or whatever. You kept a time that's pretty good. We've got time for questions now because the next talk is Martin. He's not due on until 12. So if anybody's got a question, they can unmute. I think they should be able to unvideo as well, or start their video and ask a question. Catherine, have you got a question?
Yes. Because my thing's gone.
Yeah,
we can hear you.
We can hear you and see you.
Okay. I started off using a little Fujifilm camera that I put on telescopes, and I actually, because of problems of getting adapters, I actually used the Canon EOS standard for like mounting everything together. Then I thought about putting in a teleconverter, a 2x teleconverter. Is that sensible for astrophotography?
Absolutely. We're talking about this afternoon. I will show you a picture of a Canon camera with a Barlow lens and something else, which is highly important as well, on the back of one of my telescopes. So I'll tell you that after lunch.
Okay, then. Thank you very much.
Ian, you mentioned that a power mate was not the same as a Barlow. Can you tell me what the differences are?
Well, it's got 4 elements in it rather than 2. And TeleView, I mean, they don't say quite why, but they say it works an awful lot better than a Barlow. They cost a bit more, as you might imagine, but they are the best you can have. I mean, I've got a TeleView ×2, TeleView ×4, and I've got this power mate. I mean, I don't see any obvious difference, but TeleView basically say their power mates are the best you can have.
I'll be talking a little bit about that in my talk.
Jolly good, Martin.
Comparing star tests on different types of Barlows.
Oh, brilliant! I shall enjoy that.
Yeah.
Right, we've got Tony on video. Is that because you want to ask a question, Tony?
Yes, please, if I may.
Yeah.
I have a Smith Cassegrain at the moment, but one of the things that as you get older you find more difficult to do is to get down there at the base of the eyepiece and get in a decent position to look through the scope. And I'm very tempted to go over to a Dobsonian, which I believe has a side eyepiece rather than an eyepiece at the bottom. But what are the tracking mechanisms that come with Dobsonians? Can you?
Well, the cheapest ones don't have any, and you move it around by hand. I actually like that because you then have to, well, first of all, to find things, you've got to learn your way around the sky, which I think is very good for people. Now, look, not me. We didn't really have computerized scopes until around 2000 or just before that. So I've spent most of my observing, with mounts that you had to push around and find where you're going. That's good. Having said that, you can buy now motorized Dobsonians, which I think some of them will even find things for you, and they will certainly track. So if you're prepared to spend the money, they can be very good. You get an 8-inch one perhaps, or even 10. Again, I say the eyepiece is nice and high up. I mean, in principle, though, if you have a Smith Cassegrain, do you not put a 2-inch star diagonal at the back? Your voice is gone.
Yes, I have used star diagonals. The thing is, when you start loading Barlows and other things onto your star diagonals, I find the quality of the star diagonals I'm getting from Celestron are not particularly good. They don't stand the weight very well of other things that you pile onto the.
I think you could be, well, there are better makes, and I won't say what they are. I think Zeiss make one for an awful lot of money, but no, you can get some very good ones. Teleview makes some superb ones, I might say. So look, I'm not saying I'd give up your Smith Cassegrain because they're very useful telescopes, but I wouldn't stop you buying yourself an 8 or 10-inch Dobsonian because they're lovely telescopes too.
Thank you very much. Thank you.
John Morrill, have you got a question? Yes.
It's half a question, half a comment, really. In the early days of Schmidt Cassegrains came out, I think the designer said that the worst thing he ever did was make the primary mirror movable by a large amount, because the performance of the telescope falls off very drastically away from the designed back focus position.
Absolutely true. And you can you can't find anything about that on the web. It's worried me a lot. It really does. There can only be one separation between the primary and the secondary to get the optimum performance. And I think they do actually tell you get this right, how far from the back of the scope, the mount, your eyepiece or your camera in particular has to be.
Yes.
And if you can get that right, then probably when you focus, you've got the separation correct. And
that's the reason I believe that they've got that funny flat mounting face on the back for the adapter. And it's that point that the focal position's measured from. I
think that's right. I have read recently what that number is, but if you look in the specs of these telescopes, they do tell you. It might be,
I think the Celestron Edge show what it is, and there's actually a paper on it.
Yes, that's right.
So my older 8 GPS, they've never quoted it.
No, that is a problem. It's something that's worried me quite a lot, and I've almost seen nothing about it written about it on the web. I really haven't. I can see Simon Lavington behind you, and the duty controller on your picture.
And the desk that's probably got a preservation order on it, hasn't it?
That is quite a long time ago. I designed some of the electronics in that.
That was when was the RAS meeting in Manchester? It was then.
Well, it's a long time
2000.
ago.
Yes.
Yes. No, there's some of my stuff's in that. I'll tell you. Doesn't matter.
I've got another picture for you later on, Ian. So keep watching.
Right.
Of something else you designed.
We've got Steve Hubbard has appeared on video. Have you got a question? He's frozen. No. I just saw your video. Any?
I had a comment about following up
ahead.
what Ian said there.
Martin.
A lot of planetary images who use Schmidt Cassegrains will lock off the primary because you try and change the focus. You often get image shift and a change in collimation of the scope, and you really don't want to be changing the collimation. You want to get that right, and then lock that off, and then they do focus by changing the distance, by basically moving the object, the focuser back and forth using a Crayford type focuser on the back of the scope.
Yeah.
rather than by moving the main mirror. But yeah,
That's
you
exactly what I was saying. It's by far the best way.
yes, and then you can set that at the optimum, lock the mirror at the optimum separation. That fixes the focal plane, and then you just move your camera or your eyepiece to that correctly placed focal plane.
Yeah, absolutely.
But Schmidt Cassegrains also suffer from a problem called spherochromaticism, and they are optimized in the red. So they use a red laser to set these up, and they're optimized in the red, and they'd be much better off if they're optimized in the green, because it's the green that dictates the, primarily dictates the resolution in a color image. And the blue can be noticeably affected by this spherochromatism issue.
Oh, I didn't know that. Thank you very much.
Yeah,
I think that's part of having the primer in the wrong place as well. From what I remember, the paper on the, I think it's the Celestron Edge has got a paper on their website that talks about that.
okay.
Okay, Catherine, you've got another question?
Yes, this is my SCT.
Oh,
Lovely. Aren't you
And
lucky?
and it's very difficult to balance on my Iopton telescope, on my Iopton mount. It's got minimal friction on it, and it's very easy to get out of balance. And even though when I use a little 178 camera on the back here, and I can just about balance it by putting another weight on the front, but I think I can push it forward a little bit. But when I've got a big camera on the back, like with the 26 megapixel sensor on it, I can't balance it. The only way I thought around it would be to put a different plate on the bottom, so I could push it right forward on the mount. Do you have any thoughts about this?
Well, I'm sure Martin has as well. Basically, I've seen people that put something near the front, which they can actually put a little counterweight on and move it back and forth.
I've actually done that.
Well, that's what the best people do. You must be good.
But I was actually, but even so, I have like one kilogram on the front. It isn't enough. I think it's because of the length of back focus on it with the moments.
Yeah, I'm a bit surprised it won't balance. I would have thought with the 1 kilogram on the front, it jolly well ought to. Look, I've got an RC, and in fact, the camera is 10 inches out the back, and that's incredibly hard to balance as well. So it's not as bad with one of the Schmidt Cassegrains. Well, look, all I can say is that's what people do, Martin can probably comment on that as well.
Yeah, I mean, can you not extend the weight further beyond the front of the telescope? So
it basically goes about as far as it will go. It's one of those little barder ones.
okay.
I'm on a little saddle, and I put my finder scope. My finder scope goes right in the front.
Well, that's good.
And not finder gyroscope goes right in the front.
Yes.
For X-ray. The only thing I could possibly do is shove it right up in the mount a lot more for the balance.
Well, that's what I have to do with my Ritchie Crescent. It's almost at the very end of the mounting, the Vixen mounting thing.
Yes, I've been thinking about replacing this and putting a longer one in there, so I could push it even more forward to balance my camera.
That will take away your nice handle. I mean, they're beautifully made, those Edge HD ones.
Yes, yes.
I think we've said what we can, but best of luck.
Anyway, thank you very much.
Rachel, you've appeared. Have you got a question?
Yeah.
No, I'm fine.
Here you go. Go ahead, Rachel.
Said no, I was just listening. I was just checking in.
All right. Okay. So,
Thank you, Ian.
That's all right. Good to see you.
I must say, Ian, I was very impressed with your Earthshine image there. That was an image that, you know, it wasn't a composite image between the earth shine and the crescent.
No, it was not. No, I have put them together to make a composite. That was absolutely as it was. And I don't think you could do it with a telescope that, you know,
no,
that was much different than that one. That's one of my best photographs I've ever taken, I think. So,
Ian, could you make me the host again in your little
now,
three
how do
dots,
I do this?
little 3 dots in a blue square?
Yeah.